Hey, thanks for watching. So we're going to look at what the coefficients actually mean in a balanced chemical equation. So this was the equation we looked at last time, and we put a coefficient of 2 and 7 and 4 and 6 in there in order to balance that equation up. And the question is, what do those 2's and 7's and 4's and 6's mean? Well, one interpretation of it is that there are 2 molecules of C2H6 that react with every 7 molecules of oxygen. So we can write an equals, or we can write a colon there to show it is a proportionality. So that's one way to interpret it. And we can take this and we can multiply it by any number we like. So we can go ahead and we can multiply by just some kind of random number I've just thought of. So 6.022 times 10 to the 23rd power. And what does that give us? It gives us 2 times by 6.022 times 10 to the 23 molecules of C2H6 will react with 7 times by that random number, right? 6.022 times 10 to the 23 molecules of oxygen. So perfectly fine, right, as a ratio. Oh, yes, okay, I didn't pick this number completely at random, right? What is this number equal to? That is Avogadro's number. And when we've got Avogadro's number of something, we refer to it as, do you remember? That's right, we refer to it as a mole. So we can say 2 moles of C2H6 are needed to react with 7 moles of oxygen. And so we can kind of use this as a ratio, or we can use it as an equivalence. We can say 2 moles of C2H6 are equivalent to, in this chemical reaction, 7 moles of oxygen. And why do we often write it like that? We can use this as a conversion factor. So we can use it as a conversion factor. Now, before I move on, we can generate these other conversion factors fairly easily. And I always like to take my fingers here and let's see, I'm not sure if I can get 2 fingers to appear on here, but let's say I want to know how this C2H6 is related to, say, CO2. Then I can go ahead and I can say, well, 2 molecules of these will make 4 of these. Or if you like, 2 moles of this will make 4 moles of this. So I can write that as a conversion factor. And all you got to do is really just point to anything you like on this screen and get the conversion factor. So I'll do one more here in a second, but we can say 2 moles of C2H6 are equivalent to, or will beget, or will form 4 moles of carbon dioxide. So if we wanted to know the oxygen to water ratio, we could say 7 moles of oxygen go into the reaction and out comes 6 moles of water. So we just literally point and we can create them any way we like. So what can we do with this information? Well, maybe we want to do a conversion. So maybe we want to say, if we've got, say, 1.6 moles of C2H6, and we want to know how many moles of CO2 we can get from that. We can now set this up as a conversion factor. How are we going to do that? Well, let's clean some room at the bottom. So we got 1.6 moles of C2H6, and we multiply by this as a conversion factor. So the question is, what goes on the top, what goes on the bottom? Well, we want moles of C2H6 to be gone, so we're going to put moles of C2H6 on the bottom to cancel them out. So that is our 2, which we got from pointing to our coefficients. And what's on the top? On the top is our 4 moles of CO2. And if we just take a moment and we cancel out, see, those units are gone. And at the end of the day, we'll get the answer. And I think I can squeeze it in there maybe. So essentially it is what? 3.2 moles of carbon dioxide. I wasn't joking when I said squeeze it in there. So very good. Okay, let's do another problem. All right, so here's a problem for you. So if you already know how to do this, you can skip on. Otherwise, this is an excellent problem. So C3H8 is propane, and it burns in the presence of oxygen as the equation above, which is unbalanced, by the way. And my question for you is, how many moles of water can we make from let's say 7.2 moles. Actually, let's make that 7.20 moles of propane. And so this is a 2-part problem. So you have to balance the equation, and then you have to form the molar ratios, and then you have to put it all together. So maybe it's a 3-part problem. So pause the video and have a go, and then we'll check back here in about 5 seconds. All right, so let's balance the equation. So I'm going to kind of balance this equation a little lickety-split here. So I can do this probably in my head. So I got 3 carbons here. I got 1 carbon here. So I can fix that by changing this coefficient to 3. I've got 8 hydrogens here. They only appear in water 2 apiece, so I need 4 pair in order to have 8 hydrogens. And the last thing is oxygen. So I've got 3 2s, that's 6 oxygens there. 4 1s, that's 4 over here. 4 and 6 make 10. So if they come in pairs, how many pairs equal 10? And the answer is 5. So this is a balanced chemical equation. At this point here, I need to know the relationship. So I need to get my fingers out, and I need to point at, let's see, I'm going to take moles of water and moles of propane. So I need to point at them. So I've got propane here, and I got water over here, and you can see there's no number written here, and there's a number 4 written there. So what do we do with that information? And, so what is it? That would be moles of C3H8 is equal to 4 moles of H2O. And remember, there is an implicit 1 here. So although we don't write the 1 in, we have to remember it's there. Like we don't say we have 1 finger up, we'll often say a finger. So we don't say 1 mole of C3H8, we say a mole of C3H8. But now it is here. We have everything we need to finish off this problem. So let's go ahead and do this in blue. So we've got 7.2 moles of C3H8. We set it up as a conversion factor problem. So we want to put the 1 mole of C3H8 on the bottom because it needs to cancel, and we put the 4 moles of water on the top because we need to be left with moles of water. And before we go too far, right, we can cancel these units out, so that looks great. We're going to be left with moles of water, so that is even more hunky-dory. So let me just write the units here, and let me grab my calculator and check this out. And the answer is 28.8 moles. I realized when I paused it, I could actually do that in my head. 7 4s are 28, 4 2s are 8, so 28.8. Significant figures. It's probably worth mentioning here, significant figures, I suppose. 7.20 technically has 3. The ratios are perfectly exact, right? So it turns out they are counted. So if you count things, right, there's no error. If you look at 5 fingers on your hand, it's not sometimes 4, sometimes 5, sometimes 6. It's always 5. So those are exact. So at the end of the day, I need to have 3. Actually, my calculator, if I'd used it, would have just said 28.8. So even if I had forgotten the significant figure rules and just wrote down my calculator's output, I would have got the right answer. Maybe for not the right reason, though. So very good.